My name is Armin, and in this session, I'm going to talk a little bit more about the hardware details of Project Aria and some of the challenges of doing on-device computation on Project Aria devices or AR glasses in general. So a little bit of a different talk. Just to recap, we built Project Aria to be able to understand the magnitude and the diversity of the data we can see from egocentric point of view, and to be able to do research on it. So you've learned about the kind of research this data enables just in the previous talks. So we're going to now talk about a little bit on the hardware, and we will learn the challenges. So we will answer one of the questions about what are the open challenges. So you will get to see some of them here. So here is the outline of the talk. First, I'm going to go through the hardware details, and then over the constraints on the devices, and then finally, we're going to talk about the on-device compute challenges. Let's jump right into it. So this is Project Aria device. You've all seen the components. Let's go over them one more time. The device has Wi-Fi and Bluetooth connectivity, and also GPS receiver. There are two SLAM cameras that have wide field of view. There's one RGB camera for AI and machine perception purposes. There are two IMUs, a barometer and a magnetometer, 7 microphones to capture spatialized audio. There are 2 inward-looking eye-tracking cameras. And there is a chip, a Qualcomm chip, Snapdragon 835 for compute. We have 4 gigabytes of main memory on this device, and also 128 gigabytes of flash for storage. The battery has the capacity of 2.5 watt-hours, and the device weighs around 70 grams. Now, with this battery, you can run the device on standby mode for 30 hours, but as soon as you start recording, you will kind of drain the battery faster, and it will stop sooner. So the configuration you see on the right is one of the recording configurations, and on that configuration, it will take 1.5 hours to drain the battery. And keep in mind, there is no on-device compute happening here. This is just for recording. If you do want to do on-device computation, it will drain even faster. So here's a snapshot of data captured by Aria. So these are the 2 high field of view cameras, the SLAM cameras as we call it, the RGB camera. These 2 cameras are showing the eye. As you can see, 7 microphone signals. You have IMU, inertial measurement unit, accelerometer, magnetometer, all of those signals. And we also look at Wi-Fi and Bluetooth connectivity signals, like the RSSI, received signal strength indicator. So all of these are useful information. Let's add a little bit more perspective on the hardware details we just saw. I'm comparing Project Aria device here with 2 more devices. We have Ray-Ban Stories from Meta. This is a smart camera. It captures pictures, videos. You can listen to music, to podcasts. And then Quest 2 is one of our virtual reality devices. So Project Aria at 70 grams is slightly heavier than Ray-Ban Stories, but it is still pretty comfortable, and you can wear it for long periods of time. The RGB camera on Project Aria has higher resolution than Ray-Ban Stories, but not as high as modern smart phones. In terms of the compute chip, again, we have Snapdragon 835. This is the same chip we use on Quest 1 device, which is an older generation of Quest 2 shown here. Quest 2 has a Snapdragon XR2. Now, 835 is a few generations older than XR2. And some sources say the processors are at least 2x faster on XR2. So that should give you an idea of how powerful or how not powerful the compute on Aria devices. In terms of battery, again, 2.5 watt-hours. This is usually about 1 order of magnitude lower than a smartphone. All right, now onto the constraints and the limitations. Again, we're going to talk about general device constraints that exist not just for Aria, but also for AR glasses. So there are 3 top constraints. So first of all, it has to be small. Second, because it has to be small, we don't have enough battery there, so the power is going to be limited. And then, because it is small and we are wearing it, you cannot allow it to get hot very much, so there's a thermal limitation. You cannot dissipate a lot of heat, which in turn, again, limits the power you need. So let's look at them one by one. So what do I mean by form factor? So again, the devices need to be small, they need to be light, and they need to be socially acceptable, because what we want is to be able to wear them everywhere and any time. So, something like Quest 2 that I'm showing here, you cannot wear this and walk down the street. It's just not, it doesn't work. So that's one of the things. So one more thing is that this form factor actually applies to everything, including the sensors, the camera sensors, for instance. You want them to be pretty small, but then you lose some resolution because of that. So then in turn you lose utility. So there's a interesting trade-off that you need to solve when thinking about form factor. Next one is thermal. So the thermal limitations of AR glasses are much more difficult than laptops or smartphones for 2 reasons. One of them, again, form factor. There's just not enough space for the heat to dissipate. And second, there is the glasses will touch sensitive skin, so you have to be very careful. So in general, devices, these external surfaces of the devices, you want them to be below 50 to 60 degrees to avoid burns. But for these devices, you want even lower because, for instance, the temple areas are very sensitive to heat. So if you have a glass with excessive heat in that area, it will be very uncomfortable. So again, very limiting. So the last one, again, also related because of the small size, we have small batteries, so not enough energy, and we cannot dissipate a lot of power because of the heat. So all in all, it turns out that about 1 to 2 orders of magnitude, the power available to you on an AR glass is about 1 to 2 orders of magnitude less than cell phones. One thing to note here is that battery technology will improve, but that will only improve the capacity, which makes it to energy, but the power limitation still remains because of heat dissipation. So that's one thing to consider. I'm going to go over one more constraint that I did not list on the top 3, and that's latency. So sometimes your application needs low latency, or high speed. Imagine a scenario on an AR glass. You want to show a virtual object, let's say on that table, and if I move my head, I want to be able to see it consistent with the real objects around it. This means that I need to be able to track the head very, very quickly. So, and if I add latency to that, then it won't feel real. So this is actually a big challenge because now you have to choose, do I run this tracking on the device, but there's not enough compute power? Do I send it to a cloud? Then you hit the latency and the power requirements of sending this off the device. So that is an interesting challenge. Of course, for the applications that don't require low latency, you can rely on offloading the compute somewhere else. Before we go to the challenges, I wanted to call out on one thing I call the elephant in the room, and that is the display. So AR glasses should have displays. And as we know, displays take up space. They consume power. So on your cell phone, like the majority of the power goes to the display. So then we had to make a choice because when you add display to an AR glass, all those challenges become magnified because there's this big component consuming the power. So because in Project Aria, our goal was to understand the type of data you will see from AR glass point of view, we decided to not put a display on it. So we basically compromised, and instead we got the form factor and the sensor, the sensor suite that we just showed. What do we lose? as a result of this is that we will not get real-time user feedback or any interaction from the user with the world. It's just a data collection device. All right, now let's focus on the challenges of on-device compute. Again, we briefly mentioned this, but let's see why it is important and what we can do as algorithm designers, as hardware designers. What are the challenges there? First of all, why do we need to run something on the device? So I mentioned one scenario. Maybe you need low latency. So the head tracking scenario with virtual object is one of the things. Maybe the power you need to send this or offload this off the device is just too high. So you cannot afford to do that. And maybe the user just prefers the data to remain on the device. So in all those scenarios, we cannot offload. And we have to rely on the silicon that is available on the device to do the computation. Again, this is a challenge. So looking at that head tracking scenario, can we make it happen? Can we run with such a limited power a head tracking algorithm that is accurate enough for our purposes? And open challenge there. For a long time, and this still happens, algorithm designers, software designers have relied on what we call technology miniaturization. So the CPUs get smaller and faster, and you just rely on this, getting higher density and getting more power or compute power on the chip to do more stuff. But for AR glasses, we cannot solely rely on this because the amount of benefit you get from it is not much. Is not enough because you've probably heard end of Moore's law, end of Dennard scaling. These are some of the terms you may have heard. So all of those mean that as silicon technology grows, the amount of benefit you get is not much. So we need to find other ways to make the silicon more efficient. Here I'm showing the spectrum of computing platforms with flexibility versus compute flexibility and compute efficiency and the trade-off between them. And on the top left here, we have the most common one, CPU. It's very flexible. You can do everything with it. But unfortunately, it's the least efficient. There's another famous point here, and that's GPU. GPU is also pretty flexible, and it outperforms CPU in a lot of cases, but also not very efficient. Now, of course, if you hit the scenario, what you can do is you reduce some utility from your application. You change the application, if you're thinking about a neural network, fewer weights or whatever it is, you trade utility with power. But if you want to keep the utility and make your compute more efficient, you have to go maybe somewhere on the other side of the spectrum where we have custom silicon accelerators. So what is a custom silicon accelerator? It is a piece of silicon that is designed to execute only one task or one set of tasks. So if maybe it's a linear algebra unit or whatever, maybe it just does tracking. So it could be at different levels. And it's very efficient. It's the most efficient you can get with the silicon. By the way, there are other names for custom silicon accelerators. There's hardware accelerators. There's ASIC, application-specific integrated circuit. There's hardened silicon. All of those are kind of loosely referring to the same thing. And there are other mid-level points here. Like one example is FPGA. Some of you might be familiar with this, field programmable gate arrays. And some other, what we call domain-specific accelerators, like DSPs or CNN accelerators. So depending on your use case, you may want to be somewhere in the spectrum to trade off flexibility and efficiency. All right, we talked about compute. Of course, compute is very important, but we should not forget about the other components in the system. So in addition to compute, we usually have sensors, storage, communication links, and all of these consume power. And it is actually a common scenario that they all consume relatively high power, and none of the components dominates the power. So it's not a good idea to focus on only one of them. I mean, you should focus on one of them and reduce the power, but that's not enough. You have to consider the whole thing together. So that creates an interesting challenge because, again, thinking just about compute, making compute better, but not thinking about sensor, it's not going to win. So you have to consider all these components together, and that's another open challenge, that you want to always be optimizing or co-optimizing the hardware and the software or the system and the algorithm together. So this is, I guess, one of the more important ones. Just to wrap up, I want to leave you with three key takeaways. AR glasses have strict form factor and power constraints. It should have been obvious, but just repeating it. And one way to overcome this is to make the silicon more efficient, and that is by using hardware accelerators. And then lastly, you should consider all the system components and not just focus on compute. With that, I wanted to thank you for being here and thank the great team that we're working together, and I'll take questions.
The glasses, or send it to the real phone, or send it to the cloud?
What type of models, you say?
Yeah, what parts of the model or what types of tasks that you foresee that?
Good question. So
for these different levels.
Yeah, so there are different aspects to consider. The easiest one would be latency. So if you need something low latency, like it needs to be very fast. And again, that closed loop of tracking your head and showing something on the AR display is one of them. So those probably you want to be running on the device. And the other thing would be frequency. And the reason I say that is the amount of data you upload matters in how much power you consume. So if there is an application that runs let's say at 100 frames per second, if you want to pump out this 100 frames, like without doing any compute, just raw frames or compress them, but still you want to send them over wireless. Wireless is orders of magnitude, like per bit, it consumes orders of magnitude more power than doing some computation on that bit. So you want to be able to kind of balance that. An application that doesn't need a lot of low latency and let's say runs every minute, that's another scenario. Probably you want to offload that.
I'll just steal the microphone here. That was a great question, by the way. The other big factor Armin touched on was where the data locality. So models where inferences need to be local for either privacy, security, or power and latency. And these are the new ones, really, that are worth considering, because we may well be able to process and send data to a cloud, and it may be within the regime of it's okay, high latency, it's okay, low frequency, but it may not be the socially acceptable, or there may be an expectation around that data sitting only with the user on their device. And there may be no technical reason for it other than social acceptability. And that's something that we have to look at how we break our models down so they can run parts of them locally for the local data. The other factor I think that's really interesting to consider is the continuous online learning problem, where you might have models that need to be fine-tuned for your surroundings, for your personal data. It can mean like your home setting, it can mean how you speak, etc. And those also need to be optimized for on-device compute as well. Yeah, it's a big topic, and perhaps still very new to a lot of teams. But that will become probably sort of like a big research challenge as to how to break those models into on-device, edge, and cloud. Great question. Thank you.
Thank you.
As a follow-up to that point, I wonder if there's in terms of acceptability, if there's a nice acceptable middle ground where the compute actually happens on other personal devices like your phone. Would the compute there be powerful enough to do these kind of things while not compromising privacy of any sort?
Yes, absolutely. So as soon as you go off the glasses and you hit something like a cell phone, you're already like I mentioned, or 1 to 2 orders of magnitude more powerful. So yes, if you can afford to do that. But again, you have to consider, so that eliminates the privacy constraint, but the other constraints that I mentioned, latency and power still remain. So what is the wireless connectivity? And it matters. Like, is it some of the standards are slower, so you don't get it, or if the device is in your back pocket, then you lose kind of bit rate, and all of those are things to be considered.
Yeah. All right. Thank you.
Of course.
So from your presentation, I understand that right now all the computation is happening in the cell phone instead of on the XR chip on the glass, right?
You're talking about Project Aria devices?
Yeah.
Yes.
So in the future, do you have plan to use the computing power on the phone or on the device, or you already designed some accelerator for that, or any plan for this?
So you're talking about the future of Project Aria.
Yeah.
Well, so here's the thing. As long as the device is only data collection, then some of these constraints, like the latency one, will go away. So you actually prefer to do it, to do everything off the device. The only times you will need something on the device is if you need a user feedback. Which we don't have it in Aria. So if that changes, like at some point in future, if we want to do user feedback, then we can do on device.
I mean, if I can just add one more point in here.
Sure.
As we look to, I'm gonna try not to step on that again. As we look towards like really true AR use cases that are for continuous all-day data capture, Project Aria right now is not for all-day data capture because of all the constraints mentioned. It just is very likely, if not absolutely certain, that we will have to do some computation on the device because we can't just stream the raw data all day, right? I forget exactly, we said like 4 gigs per minute, I think George said earlier of data for at least Quest. You can imagine the order of magnitude for Aria as well. So it just probably will not be feasible that you can have like 8-hour collections, 12-hour collections where things are really going in terms of raw data stream out. So that's kind of an important future thing, I think, to have in mind.
Okay.
Yeah, in terms of developing models for this project, for these glasses, so do you recommend maybe to start with the heavy net first and then sort of optimize your way down, or start with the smaller models with sort of, having all those constraints satisfied early on during the development?
That's a very good question. I will give you my opinion, but I'm not sure. I don't have data to support this. But I would say you want to start from smaller ones, and then do a lot of techniques that hardware-centric optimizations like quantization and adding sparsity. It also depends on what is your target device. If it is just Aria, it has only Snapdragon. But if you think ahead, there will be more chips like the XR2 chip from Qualcomm actually has a CNN accelerator, and then that changes the balance a little bit, if you will. But my suggestion is to start from something small.
Okay.
All right, let me advocate for the exact opposite. I think, so we're all one team, so we have a diverse opinion here, and Armin's the expert in actually power optimizing these things. As we saw with Julian's talk, the reality is we have networks with billions of weights as a component for a front-end system. And realistically, we have not been able to demonstrate, say, clip-like performance on tiny networks. I mean, if anyone's been playing with the mini DALI models, you know where that goes, and it's still good, but they're massive models still. So I think it's a really good question, because at the heart of it, I think there's two-pronged answers, and then there's the reality that you've still got to power optimize. That's okay, we'll solve it. It's probably the power here. The approach that we've been taking is to look twofold. Number one is to ask, fundamentally, where's the redundancy in the information stream that's coming into a device? Where's the redundancy, for example, in sensing an inference, such that, for example, between this frame and this frame and this frame, the concept of processing per frame is replaced with a consistent model of reality which is being built up to date and is updated with inferences that are necessary because the model is potentially shown to be wrong. That's a different paradigm. It's very different from starting with a big network, processing all of the frames. It says, fundamentally, shift your perspective to a model of reality that is being inferred, and then do efficient updates on that model. And the initial model may be expensive, but the updates are effectively cheap. Now, when we get in there, then what you've seen is the teams sort of showing what that starts to look like. Once you have SLAM, you can start to think about 3D frames of reference. You can start to cache inferences from convnets that basically feed forward into a 3D space and decode from that. That's that fundamental view. But from a point of view of how big are those front ends, they're still massive, and would not run today on, for example, the Qualcomm that is in Aria today. So I think if a capability doesn't exist at all, start big, make it work at all, but make it work at all in the frame that this is a 3D world with 3D video data versus make it work on a single frame. And that's the other shift, basically trying to build what might be very big models, very big networks, but they fundamentally work on spatialized data. Then you optimize, and that's the key, of course, where in the end, if you don't, it will never be working in real time on a device. Yeah. Great question.
Okay, yeah, thank you very much.
So will you ever consider a wired connection between your glass and your phone? Because I imagine that would relax a lot of constraints, and some people do still use wired headphones.
Yeah, so that's a very good question. It's a whole spectrum of usability versus power limitations. So again, if you wear those Quest devices, if you agree to use a Quest device, then you can do everything on them. But they're very big, so you won't be doing it. So if the majority of users agree that okay, a wire coming like this coming through my clothes to my phone, is this okay? Then sure. But it's a decision. It's a trade-off that requires more research. But yeah.
Yeah. These are brilliant questions.
Difficult.
Yeah, very, very good questions. So you can use Aria plugged in. So the battery, has a cable. That's how we charge it, etc. But the key concern is not actually the battery draining. It's power dissipation. Thermal dissipation on a glass's form factor is the problem. And even if it's wired, if you had a wired unit, which is certainly a problem when you start to see how thick the wire would need to be for the certain data rates and so on, even if it was an optic fiber cable with power. It's not like a headphone wire. That's not the problem. The problem is actually dissipating if you wanted to use higher frame rates or for longer periods of time, or running things on the device. So what's kind of interesting is the thermal footprint of Aria, just as a sensor and compression, using that chipset today, is really at the limits of glass's form factors. If you want, 1.5 hours worth of recording with the kind of profile that we showed, on the order of, 10 frames per second off 17 odd sensors, etc. And that's physics. So at the end of the day, all we can do is start to say, how could we prevent sensors needing to even be turned on? How do we even turn off computation because it's redundant? I'm seeing the same room and all that changed was a few bits of information. That's the actual shift, and with a cable or without, we still have that problem to solve. And that's the machine perception problem in the 3D space. Yeah, great questions.
So my question is, what's the most complicated model in terms of the type of layers or number of parameters that you have already implemented on the Aria device, and what was the struggle with that particular model?
So I don't think I can disclose that. Can we say? but I give you a hint. Like it's the amount of memory you have there. Like the main memory could be it's I think 4 GB main memory. That is one of the biggest. Usually memory is the biggest limitation. So 4 GB is where you can fit your weights and your activations.
So it's mostly about the number of parameters and not the type of layers, is it?
It depends on. I think there are both limitations in terms of compute power and in terms of memory. I think the memory will limit you sooner than the compute will limit you. Yeah.
So I have one more question. So I see a lot of papers coming out of Meta on neural architecture search, right? So have you guys considered it as a solution for this particular project to solve any of the constraints you have?
Yes.
And that's it.
Thank you.